Hello everyone. In today's video, we'll try to solve a linear regression example. We'll model this linear regression example as an optimization problem. And let's get right into it. The first blob, the first block here, we will import a few libraries. It's NumPy, Matplotlib, and Pulp. Then we would want to generate some data. We set a random seed using NumPy. We would want to generate 100 data points. We generate random 100 values and save it in a variable called x. For the target variable or the y variable, we would want to model this as a linear equation. So 2x plus 1 plus some noise. And this noise will add some variability to our data. And if we plot this data now, this is how it would look like. This is the x-axis, this is the y-axis. Objective would be to find a line, a best fit line for all of these data points. Now, before modeling this as an optimization problem, let's quickly look at an example on a website called LibreText Mathematics. Here, they want us to solve an equation x plus 2, the absolute value is equal to 3. The way that they suggest to solve this is we break down this equation, absolute value of x plus 2 is equal to 3. We break down this equation into two. X plus 2 is equal to minus 3 and x plus 2 is equal to 3, right? The solution is inconsequential, but this idea forms the crux of modeling this linear regression as an optimization problem. So now we would want to choose an error metric. In this case, we'll choose the absolute mean error as the loss function. Now our objective is to minimize this loss function. Say we would want to fit a line, y is equal to ax plus b, a is the slope and b is the intercept. A and B are the values that we will find using linear regression or optimization. And of course, our objective is to minimize the sum of absolute differences between the predicted variable y and the actual variable y. Right. So now this is a mini-max optimization problem. And we can model this as minimizing the summation of absolute differences between y, which is the actual values, minus the predicted values ax plus b. And for the sake of this conversation, we would want to keep a and b positive. This is the line equation that we are trying to fit. We have chosen this explicitly because we would ideally want this a and b value to be as close to 2 and 1. Now, one issue here is this is not a function is not linear because of the absolute symbol. However, we can linearize it by introducing auxiliary variables. However, if you look at this equation, this is very similar to the one that we saw on this website, maths.libretexts. And here, one way that they suggest us to rewrite this equation is by splitting the values of plus or minus 3 as minus 3 and plus 3. So we can do something very similar here. We can introduce the auxiliary variable t for all I, and I ranges from 0 to n, where n is equal to 100, the number of data points that we have. And we can say y of I minus a of x of I plus b, this is the delta, is less than or equal to t of I. And if you can imagine here, we can write a lesser than or equal to sign, and it should be between minus t of I, right? So if we take this equation and if we take this equation, we can write y of I minus a of x of I plus b is less than or equal to t of I, and minus y of I plus a of x of I plus b is less than or equal to t of I. Now this is a linear problem and we can solve it using linear programming. The problem itself is very simple to code. We we declare slope as a variable with lower bound 0. We declare intercept as a variable with lower bound 0. And then for each I, we generate n number of t variables. That is the auxiliary variables. We define the objective as minimizing it. And then our objective function is to minimize the sum of all auxiliary variables, that is t of I. Our constraints are going to be this. We would want to find the minimum value of actuals minus predicted. And then we can call solve, and we can print out the slope and intercept. So in this case, the slope is 1.7, the intercept is 1.3, very close to 2 and 1. And if we can plot the line, this is the best fit line. We can also solve this problem using linear regression from scikit-learn. The code is very straightforward. We have the x variables. We declare a linear regression model. We fit the model using x and target variable y, and we can print out the slope and intercept. Here the slope is 1.9, intercept is 1.2. And we can also plot the best fit line for both now, the optimization problem as well as the scikit-learn. So this is the best fit lines in either cases. Hence we can see that we can also model this linear regression as an optimization problem.